Hi class, welcome to the 5.4 through 5.7 practice exam key video. And so let's start off right away with number 1. So what conditions does an oxygen gas behave least like an ideal gas? So to be ideal, you want to have high temperature and low pressure. So when we're talking about least, we want the opposite then, low temp and high pressure. The concept of an ideal gas, what that's used to explain, it has nothing to do with mass or monatomic versus diatomic, but it's just the overall behavior of how a gas acts. And then according to, now this kinetic molecular theory, a lot of times I just jump right in and not use this big fancy terms. All this is the numbers 1 through 5 at the beginning of your 5.4 through 5.5 notes. So you can review those, and it's just the theory of how an ideal gas would act. And so of those numbers, it says that gases will move randomly, but constant in a straight line motion. So they're not packed together, they don't have a significant volume, and no strong attraction for each other. Then number 4, which of these gases behaves most like an ideal gas? The key here is the smaller, the better. And so the smallest one would be hydrogen. And then number 5, an assumption again coming from those number 1 through 5s there, that the particle of a gas is that they have little attraction. To behave more ideally, you don't want them interacting with each other, and they also want to be small or have a non-significant volume. And then number 6, one reason that a gas would deviate from these ideal gas ideas is that if molecules had attraction forces together. So these questions are pretty repetitive, really nailing down the idea that kinetic molecular theory, or how gases behave, they should not have attraction to each other, they should be small, they move constant in straight line motion, and it is that they have no net loss of energy. That is true. Moving on to the next page here. So the relationship that happens between pressure and temperature is that as pressure increases, so does the pressure. So answer A would be correct. And now let's start getting into the calculations or some of the heavier problems here. And so how I approach these problems, since I don't give you the title of what's constant, what's not, I don't tell you what equation to use, is start picking apart the data to see what you have. So I have a 2-liter sample, that right there is a volume. STP indicates that we have standard temperature and pressure. So we get a temperature and a pressure. Our temperature would be 273 K, and our pressure would either be 1 atm or 101.3 kPa, depending on if there are other pressures listed. We want to make sure that the units match. We're increasing it to 27 degrees. So here is another temp, but it's in 27 degrees Celsius. And so in order to convert that to Kelvin, remember that Kelvin is equal to degrees Celsius plus 273. So all we're going to be doing is adding 273. That gives us 300 Kelvin. And then it says the pressure is decreased to 80 kPa. So here's another pressure. So that tells us we're going to want to work with the standard pressure of 101.3 kPa. And then lastly, it's asking what is the new volume. So we have another volume variable. So since we have multiples of both volume, pressure, and temperature, this is going to be the combined gas law. So P1 V1 over T1 is equal to P2 V2 over T2. So now we have to decide which ones are the ones, which ones are the twos. So you have to make sure to keep all the ones together as one condition. So initially we're starting off with a 2-liter sample at STP. So these are our ones, and then our 2 is that we are increasing it to this new temperature. Here's the pressure being decreased, and we're trying to figure out what that new volume is. Now, for the sake of working room, what I'm going to do is I'm going to move up into this area here. So this is where I'm going to start using the work of the combined gas law. So if we have, I'll switch colors here too. P1 V1 over T1 is equal to P2 V2 over T2. We are looking to solve for V2. So this is what we want to solve for. We'll highlight that in purple. And so what we want to do is move away our pressure. This is going to go to the denominator. This temperature is going to go to the numerator on the other side. So our newly arranged formula is P1 V1 T2 all over T1 P2 is equal to V2. And so now you just have to plug in all your variables. So we have 101.3 kPa. I'm not going to write the units just to save room, but proper way to do it, write units. And then V1 is 2 liters. And then we have T2, which is 300 Kelvin, all over T1, which is 273, times P2 of 80 point kPa. And so when you calculate this out to get V2, the correct answer here is going to be C. All right. And so the next one is also a calculation. So if you need to record this data, pause. I'm going to erase it so I can give myself more room to do number 9. All right. So now looking at number 9, we have 60 liters. So again, another volume at 546. Here's a temperature cooled to a new temperature. So I'm already going to call that one T1 and T2. This is at constant pressure. So now we know we don't need to use pressure. And so then lastly, the question's asking for the new volume. So V1 and V2. Now all that's given to you is the combined gas law. So I'm going to move up here. P1 V1 over T1 is equal to P2 V2 over T2. Now, I said that pressure is constant, so take pressure off of both sides of the equation. So now you're just left with V1 over T1 is equal to V2 over T2. And so if we're solving for V2, we just want to make sure to move T2 to the numerator on the other side. Our new equation is V2 is equal to V1 T2 over T1. Plugging in our values, we have 60 liters times 273 Kelvin all over 546 Kelvin. This gives us an answer of 30 liters. 10. This is talking about the relationship between pressure and volume. And so how I get there is it's asking about a confined gas at a constant temperature. And so if we take a gas and double the pressure in a confined container, what's going to happen to the volume? And so strictly thinking about the relationship, I'm going to use the ideal gas law as an example. Don't worry about the nRT right now. But if we were to solve for pressure or volume, so either one of these, let's say pressure, what ends up happening is both of them are going to move down to the denominator in either way. And so what this ends up showing is if we get rid of all the extra junk, think of it as pressure would be equal to 1 over V. And then thinking about it now in the case of volume, if we were to solve for volume, we would want to move pressure down, and you'd get volume is equal to 1 over pressure. And so in our case, this explanation of a relationship kind of helps with reasoning. And so if we say that we have double the pressure, so imagine we multiplied this P by 2. What ends up happening to the volume? Well, think about it as instead of 1 over 2P, think of it as V is equal to 1/2 P. So what you end up having in order to keep things consistent is a halving of volume. All right, number 11. I'm going to do the work for that one down here. And so, again, analyzing what we have. We have 40 milliliters volume, 20 C temperature, volume, new volume at constant pressure. So we're not going to need pressure again. What is the resulting temperature going to be? So we have V1 T1, V2 T2. And so previously I already solved the ideal gas law, what the equation would look like before or after you cross off constant pressure. So initially what we're starting with is V1 over T1 is equal to V2 over T2. We're solving for that T2, so we want to get that out of the denominator right away. And once we do that, we get T2 V1 over T1 is equal to V2 over our imaginary 1. We're going to move V1 to the denominator, T1 to the numerator. Then we will get that T2 is equal to V2 times T1 all over V1. Plugging in our values, we get 80 milliliters times 20 degrees C. So calculating out what that is in Kelvin is just 20 plus 273. So we have 293 Kelvin all over V1, which is 40 milliliters. And so what you get for your answer there is C. This would be the setup. Now, the volume of a sample of a gas at 0 degrees C, temperature is 100 liters volume. If the volume of the gas is increased to new volume, what's the new temperature of the gas? So I'm using the same exact setup where I want to use this T2 is equal to V2 times T1 over V1 because we're looking for that new temp again. I'm going to go in and fill the subscripts here. And so what I'll do is I'm going to erase these numbers, and now we're just going to plug it in for the new problem. So our new volume 2 is 200 liters. Our T1, if it's 0 degrees C, 0 plus 273 is 273 Kelvin, all over V1, which is 100 liters. And so what you should get as your new temperature would be D. All right, 13. And so here, what's the relationship between volume and temperature? And that is going to be C. As temperature increases, volume increases as well. And again, you can think of the relationships in respective to the formulas, but even just memorizing the idea that volume and temperature have a direct relationship will help you. All right, 14. Which of the following has the most molecules? So this you would have to think of the ideal gas law, because I think using the relationship to reason through these can be very helpful. So which has the most molecules? Now, if you look at all the options, it's giving you a volume, a temperature, and a pressure, but notice how all the volumes stay the same. So let's not even consider volume since it's constant. And so now really all that's changing are temperature and pressure. Remember that R is just a constant. So if we were to solve this for N, or the number of molecules, we would get N is equal to P over T. So think of a fraction. If we were trying to get the largest number from a fraction, the way to do so would be increasing the numerator to make it a bigger number. And we'd want to decrease the denominator. And so we're looking for the combination now that has the highest pressure and the lowest temperature. For us, that is option D. Number 15. So now it's asking which two samples contain the same total number of particles. So again, thinking of the relationship N is equal to P over T, that will apply for this question too, because we're only considering temperature and pressure. It's telling us that all the samples are in a 2-liter container, so volume's constant again. So which two gases have the same ratio of pressure to temperature? Well, that's going to be Ne, because it's a pressure of 1/300. And CH4, that same ratio of 1/300. So they're going to have the same amount of molecules. What volume of CH4 at 0 degrees C and 1 atm contains the same number of molecules as 0.5 liters of N2 measured at 27 degrees C and 1.5 atm? So there's a lot of numbers thrown at you. And so this is kind of a two-step question here, because we're going to have to figure out the number of molecules of N2 and use that in an equation with CH4. So I'll break this down. I'm going to use the space up here to do this problem. So first we have to figure out how many number of molecules does N2 have. Well, if PV is equal to nRT, if we solve for N, that is just moving RT to the denominator on the other side, we get N is equal to PV over RT. If we plug those values in for N2, so think of N, and I'm going to put subscript N2. Pressure is going to be 1.5 atm. I'm getting that from here. Now, the volume was listed as 0.50 liters. This looks like a 2, that's an L. R, since we're working with ATM, is just defined as 0.0821, and there's a bunch of units after that guy. I'm going to drop them for simplicity. And then the temperature, now we have it listed in degrees Celsius, but make sure we convert that to Kelvin. And so 273 plus 27 equals 300. And now when you solve for the number of molecules of N2, you get 0.030. We'll leave that rounded just for simplicity's sake. Now, this strictly up above is all for N2. We have to figure out what volume of CH4 under certain conditions has the same number of molecules. So, for CH4, if we're looking at PV is equal to nRT, it's asking for volume, which means we have to solve for it. Move pressure to the denominator. Our new equation is B is equal to nRT over P. And if we plug our values in, we just calculated N as 0.030. I'm going to, again, pause if you're still recording up above. I'm going to have to erase just for room's sake. And then I'll move this up. And we'll start this one over. So we just solved for N, 0.030. R is 0.0821, that's that constant. And the temperature here is at 0 degrees C, and so 0 plus 273 is 273 Kelvin, all over the pressure of 1 atm. Now when you solve that problem, you will get 0.68 liters. All right, number 17. So what is the pressure exerted by, we have a moles. And so if you have an indication of moles, you know right away you're using the ideal gas law. But anyway, we have a temperature of 20 degrees Celsius. That's, oops, not B, that's a T. And a volume of 9.5 liters. Oops, and I'm writing goofiness now. It's our volume, and it's asking what pressure. So we don't know what this is. We're solving for P. And so if we solve the equation for P, we get P is equal to nRT over V, as we're just moving the volume into the denominator on the other side. Plug everything in, we get 1.2 times 0.0821 times, turning 20 degrees Celsius to Kelvin is 293 Kelvin, all over 9.5 liters, and that gives us 3 atm. Now, 18 is a concept question. So it's saying if we have equal volumes of SO2 and O2 gas at standard temperature and pressure, what are they going to have the same number of? And so if we think about PV equals nRT, we have equal volumes, it's at the same temperature, pressure, and R is a constant. What they're going to have equal of are N, or molecules. And 19 is just building on that. Again, if we have gases at the same volume, same temperature, same pressure, they're not going to have the same amount of atoms, because if you think about it, hydrogen has 2 atoms per every 1 argon. CO2 has 3. And so it's not going to be atoms, which means it can't be A or C. It's strictly molecules that we're talking about here. All right, 20. So this is a partial pressure question. And so remember that the total pressure, let's do it this way. Pressure total is equal to partial pressures of X, Y, Z, whatever molecules you have. So in our case, it tells us the total is 74 kPa. And so we are getting the partial pressure from oxygen is 20, nitrogen is 40, and it's asking, okay, for the only one left over, what is this partial pressure of hydrogen? So if you just solve for X, you end up getting 74 is equal to 60 plus X, so X is equal to 14 kPa. Number 21. So here, it's saying a mixture of gas has total pressure of 200 kPa. And now when it starts talking about moles, it's giving us the total moles in its parts. So if we have a mixture of nitrogen and oxygen, we have 8 moles from nitrogen and 2 moles from oxygen. So our total number of moles is 10. And so when you have to figure out the contribution from each, what you have to do is, okay, how much pressure would there be from each mole? So we would take our 200 kPa divided by our 10 moles. That is equal to 20 kPa per mole. And specifically, it's asking about oxygen. Well, oxygen has 2 moles, so you just multiply this by 2 for moles of oxygen, and that gives you 40 kPa is your answer. 22 has to do with diffusion. It's asking if they're all unstopped at the same time, which will diffuse the fastest? This has to do with density. So remember, the lower the density, the faster the diffusion. And so for our case, if you were to look up on that table at the back of your blue packet, you would find that helium has the smallest density, therefore tube A will be the fastest. All right, 23. And so I don't have the best way on solving this. This is just how I would approach the problem. So feel free to reach out to me with a better idea. But when you have a question that's saying, okay, argon makes up X amount of the atmosphere. In our case, it's 0.93%. If we have a sample, what's its overall pressure? If that partial pressure that argon makes up has a value of 6.54 millimeters of mercury. And I'm telling you, this trick I'm teaching you is something I use in life all the time. And so I like to set it up as cross multiplication. So if 0.93% is 6.54, oops, I'm setting this up upside down now too. One moment here. If 6.54 millimeters of mercury is to 0.93% of a sample, what is the pressure to 100% of the sample? And so if you were to solve for X, you would just move that 100% to the numerator on the other side, and you would get 100 times 6.54 divided by 0.93, and that gives you the answer of 703 millimeters of mercury. There will not be a question like that on your test, but I wanted to show you how to do it. And then we're not doing 24 or 25 and 26 because I dropped that out of material for this semester. And so that moves us on to 27. Using this information, answer the following questions. And so what it's asking in 27, what's a new temperature and a new pressure that will cause it to behave more like an ideal gas? And so you have to think of the conditions that creates the environment for an ideal gas. That is going to be high temps and low pressures. So all you'd have to state for this problem is a temperature that is greater than 298, and that should go this way, and a pressure that is less than 1 atm. So it would be anything greater than 1 atm would be fine, and anything less than 1 atm would be an okay answer, and anything greater than 298 would work too. 28. So now we're determining the volume of the gas. And so here is determining at STP. So when we're changing conditions, it's automatically going to be the combined gas law. So P1 V1 over T1 is equal to P2 V2 over T2. We just have to define what those variables are and figure out what we're solving for. And so our initial condition is going to be these conditions up here. So call this our P1, V1, and T1. If we're determining the volume of the gas, so what's our new volume? That means we're solving for V2. And don't forget STP. These define the new pressures and temperatures. So P2 and T2. Since we're working in ATM, P2 is going to be 1 ATM because that's standard pressure, and T2 is going to be 273 Kelvin. So solving for V2, we are moving T2 to the numerator, P2 to the denominator. That gives us V2 is equal to P1 V1 T2 all over T1 P2. Plugging in the values, we get 1 ATM times 2.5 liters times 273 Kelvin, all divided by 298 Kelvin times 1 ATM. When you solve that, you get that your new volume is equal to 2.3 liters. And so 2.3 with sig figs, because 1.0 ATM and 2.5 liters limits us. Sorry, I should put that STP, this is defined as 1.000, so that would not have limited your sig figs, so that was my bad. All right, and lastly, number 29, now determine the moles of gas in the cylinder. So for this problem, again, if you see moles, we're using the ideal gas law. And so for these pressure, volume, and temperature values, you just have to pick one of the two conditions here. I am going to work with P1, V1, and T1. So that's where I'm going to be pulling these values from. So determining number of moles, we are solving for N. So we move RT to the denominator on the other side. N is equal to PV over RT. Using P1, V1, T1, that would give us 1 ATM, 2.5 liters, all over 0.0821 times 298. When you solve for that, you should get 0.10. You would have to have that 0 moles.